So this problem is about matching each surface in their Cartesian form to a parameterization, and there are a bunch of Cartesian forms, a bunch of parameterized form. I start with the first parameterized form. My plan is basically to eliminate as many parameters as possible to come up with a Cartesian form. And so at this point, I can see cosine of t, and I see sine of t. And the first thing that I want to eliminate is using Pythagorean theorem as the cosine of t and sine of t. So how does that work? So if x is equal to 4 cosine of u, then cosine of u is equal to x over 4. If y is equal to 4 sine of u, then sine of u is equal to y over 4. Go to power 2. And then this side adds up to 1, and the other side adds up to x squared over 16 plus y squared over 16. And that's basically x squared plus y squared equal to 16. And it seems like z is not basically related to x or y. So z is a free variable. Z is free. And therefore, the answer should be this one. That's A. Now let's do the second one. B of u and v is equal to u cosine v, u sine v, and u squared. And v is between 0 and 2. And u, again, can be any variable. And it's a free variable. U can be any value in R. So now, again, I'm still into trying to eliminate sine and cosine. So here I can see if I solve for cosine of the v, I will get cosine v is equal to x over u, sine of v equal to y over u, going to power 2. I end up with a 1 in here, and I end up with x squared over u squared plus y squared over u squared. Multiplied by u squared, it's x squared plus y squared equal to u squared. Now I'm still hanging on to that one parameter, but that's not a problem because actually u squared is equal to z. So I get z equal to x squared plus y squared. And that's over here. Now let's do C. C of u and v is equal to 4 cosine u sine v, 4 sine u sine v, and 4 cosine v. V is between 0 and pi, u is between 0 and 2. Here's x, here is y, that's z. I can see that x and y have basically, they have both for sine of v, and in addition to that, x has cosine of u, and then y has sine of u. And then u is not appearing for z. One way is the recognition for all of these. Some of you are comfortable recognizing now, and this looks like spherical coordinates with rho equal to 4. But if you really have to eliminate to find things, the best case scenario is basically solving for Pythagorean. Basically, x squared plus y squared is going to end up to be 16 sine squared v, and then you will have that z squared is going to be 16 cosine squared v, and then you end up with, if you add it up, it's going to be again 16, and so that's the sphere of radius 4. So there are multiple ways of finding this, and we're just offering you one in each, basically. So now let's do D. U cosine B and U sine B and 2. And V is between 0 and 2 pi, and U between 0 and 4. First thing, and I notice is Z equal to 2, and then I notice that basically there is cosine of V and sine of V for X and Y, and therefore basically if I want to use Pythagorean theorem, I have to go to power 2 and then divide by the u every time and multiply by u at the end. So let's not go through all the process that we did before and just go x squared plus y squared, because we know how these things end. So this is going to end up to be equal to u squared. But the problem is I cannot eliminate u squared with anything else. So let's think about this a little more. Basically, we are on a plane z equal to 2, and then this is the equation of x squared plus y squared less than equal to 16, because u squared is 16, between 0 and 16. Between 0 is obvious part. And so this is actually solid, and we are intersecting it with z equal to 2. And this is the solid cylinder, filled cylinder, intersecting with z equal to 2. And what we're getting is going to be a disk. And so that's D over here. Now the last one, E of U and V, cosine V, sine V and U. V is between 0 and 2 pi. So in this case, again, I see the same pattern. So I start with x squared plus y squared. And I know this is going to end up with all my practice to be u squared. Oh, and u squared is equal to z squared. So z squared equal to x squared plus y squared. And that's the cone. And let's see, it's right here.